I've asked you people to share the email IDs. As soon as I receive everyone's email ID, I will add you. I will share the test paper with you. I will also share a drive with you in which you will have recorded sessions. Okay, and please ensure that I am keenly observing who is coming to the class regularly, who is not coming to the class regularly. So based on that, I may remove them from the group. I have just continued the classes. If you see, the last date for payment of course fee is 3rd of April, guys. Till now, I have not even brought a word of course fee into picture, right? Because I said it is not really about money. So please understand. So when sir is putting some extra time, see, I can be with my family for 1 hour 45 minutes, 2 hours, whatever it is, guys. Right? So because I think it was one of my, again, very deep interest, because I was attached to something. I wanted to do something for you people. I couldn't do. I was not able to stay on my words. Initially I was, but after that, maybe 3 4 months, I was not able to connect with you people. I thought these 40 days I can help you out in some or the other way. Okay, so that is the main vision again. So please ensure you're utilizing it. हाँ, आपको कोई भी पे करो बोल के बोले भी नहीं. I don't know, I have seen. ठीक है, I'll just cross check it if you have paid. However, I have not brought anything into course fees into picture, guys. I'll not bring it maybe for a few days, I think. So I'll share the information of that also. Okay. Is the board visible, all of you?
Yes.
Right. So we are going to deal with electrostatics. कौन है कौन है कौन है कौन है? What about marks? We will see. What about fees? We will see. Remove Hemant, it seems. Shall I remove Hemant? Yeah, tha, remove Hemant Potarla from the call. We'll remove him. Right. No titting here, huh? So we are going to discuss regarding electrostatics, guys. So in this, basically, as I have given already, you may get 3 to 4 questions from electrostatics. Now, when I say electrostatics, it is a combination of two things again: electric charges and fields, electric potential and capacitance. Usually, you will get capacitance 1 question, guys. Electric potential, electric charges and fields, you will get 2 questions, right? So 3 questions. So I can expect from these 2 chapters. However, as you solve more questions, you will become better in the subject. But in order to solve the questions, you need to know basic things. What are those basic things? You need to know what is the process of solving the question. You need to know what is the formula that has to be applied in that particular question. When you will get acquainted with these two things, if you start doing questions. So that is the very basic logic again. So we will discuss we will do the review of both the chapters, electric charges and fields, as well as electrostatic potential and capacitance, in this session, maybe for 2 hours, whatever it may be, or more than 2 hours. And post that, tomorrow and day after, we will solve questions of electrostatics. Again, Sunday I may take extra session. Now morning, afternoon, ऐसा कुछ नहीं चलेगा भाई, right? So I may take some extra session on Sunday, and I'll try to wind up current electricity, which was supposed to, I think I was supposed to give 2 classes for that, right? So properties of electric charge. So what is basically charge, guys? It is just property of matter because of which the interaction will take place, guys. So it is property of matter due to which electromagnetic interaction will take place. So basic properties of charge you need to know. Again, what will happen? I'm just underlining them, guys. Charges interact with each other. Similarly, again, charge of an total isolated system is conserved. Charge will always be conserved, guys. Conservation of charge is a basic fundamental law. Conservation of mass is not a basic conservation law, guys. So charges interact with each other. We know again. Now, here there is some contradiction again. Like charges repel each other, they have given. Unlike charges attract each other, they have given, guys. There is a possibility for like charges also to attract each other, guys. Okay. It is not necessary that like charges should always repel each other. There is a possibility for like charges to attract each other also. That will happen on the basis of induction, guys. So like charge, again, you can consider like charges repel, but it is not the only case. There is a possibility for like charges to attract also, right? Positive and negative, you can leave it aside. So charge of an isolated system is conserved, guys. So q value will remain always constant. Charge is quantized. What is the meaning of quantization of charge? Again, you take any amount of charge, it will be represented in terms of basic unit of charge, guys. N into ev, right? It as this is called as quantization of charge. So charge can be transferred, guys, right? So it can be transferred from one object to another object. right? So it's a basic case again. Charges are additive in nature. They are not going to vary with speed, guys. Mass will vary with speed. Charge will not vary with speed, guys. How mass will vary with speed? It is given as m naught divided by under root of 1 minus v by c whole square. M naught will be rest mass of electron. When it is at rest, it will be rest mass, guys. So if any charged particle is moving with a speed comparable to the speed of light, then its mass will change. However, charge of the particle is not going to change, guys. It will be invariant with speed. So charges interact with each other. Charge of an isolated system is conserved. Charge can be transferred, right? Charge is quantized. So please don't say like charges will always repel each other. They may attract each other also, right? So charge will be invariant with speed, guys. Some basic units of charge, as you can see, we have coulomb is the basic SI unit of charge. We have electromagnetic unit and we have electrostatic unit, guys. Okay, so EMU, ESU as well as coulomb. These will be the basic things again. And as you can see, one electromagnetic unit is 10 coulomb, and I can write 1 coulomb as 3 into 10 power 9 electrostatic unit, guys. It's also important again. 1 coulomb is 3 into 10 power 9 electrostatic unit, and electrostatic unit and stat coulomb both are same, guys. Okay, so different units of charge, if you remember, stat coulomb. Franklin again is also unit of charge. It is the smallest unit of charge, guys. So coulomb, electromagnetic unit, electrostatic unit, right? Stat coulomb, Franklin. These all are basic units of charge. We also have something called as frictional electricity here, right? So it's not that much necessary. Very simple logic, guys. If you take uncharged objects, what do I mean by uncharged object? Net charge is zero, but they're going to have some charge particles, guys. Whatever number of positive charges are there, same number of negative charges will be there. Suppose two uncharged objects I have taken, right? If I am rubbing, so some electrons from one object may go into other object. So this will be loss in electrons. This will be gain in electrons. So this will become positive charge. This will become negative charge. So we are charging two neutral objects by rubbing. So this type of charging will be called as frictional electricity, right? Charging by friction also we can consider. Also, one more very important property about charge is charge can never exist without mass, guys. Charge cannot exist without mass. It's very important. Mass can exist without charge, but charge can never be independent of mass. So these are basic properties of charge that you need to know, right? What are those properties? Charges interact with each other. Charge of an isolated system will be conserved, right? And charge can be represented, total charge can be quantized. Again, it is the total charge of an object can be represented as integral multiple of basic unit of charge. Charge can be transferred, right? Charges are additive in nature. Charge is invariant with speed. It is not going to vary with speed. Different units of charge we have seen, right? And we have also seen that charge cannot exist without mass. Now, interaction between the charges can be understood with the help of a law called as Coulomb's law, guys. So, interaction between charges can be understood with the help of a certain law called as Coulomb's law again. So, what is it stating? Whenever we have two charges of, let us say, similar polarity, usually again, if I have 2 point charges of similar polarity, they will repel each other. 2 point charges of dissimilar polarities, they will attract. Point charges, I'm saying. I'm not saying charges, guys. For point charges, definitely I can say 2 point like charges will repel. 2 point unlike charges will attract. It will not be true for every charged object, guys. It will be true for point objects again. So what is it stating? Whenever we have two charges, charges will interact with each other. And how will they interact, guys? They are going to interact with the force given as 1 by 4 pi epsilon naught q1 q2 divided by r square, guys. So 1 by 4 pi epsilon naught will be the proportionality constant, whose value is 9 into 10 power 9 Newton meter square per coulomb square, and epsilon naught is your absolute permittivity. It is also called as permittivity of free space, guys. Epsilon naught value will be 8.85 10 power minus 12 coulomb square per Newton meter square. Sometimes dimensions they may ask you guys related to epsilon naught, absolute permittivity dimensions they can ask. What will dimensions be? So as you can see, coulomb is nothing but current into time, guys. A into T you can write. So you will get this as A square T square. In denominator you will get ml cube T power minus 2. So what I will get, beta? M power minus 1 L power minus 3 right? T square you will get, I think you will get it as a square t power 4, I believe. Am I right, all of you? See, in denominator you will have Newton meter square. Newton is ml t power minus 2. The Newton meter square will become ml cube t power minus 2. If I send in the numerator, it will become m power minus 1, L power minus 3, t square it will become. And I have Coulomb as a square t square. So this will be the dimensions of epsilon naught, guys. Okay. Now, second, some important points they're asking. In vector form also we will have Coulomb's law, but that is not that much essential, guys. Right? What is see, whenever you have two charges, same things we study in gravitation also, guys. Only thing is charges will get replaced by masses again. Okay, so there also we will review again, but basic things you should be aware again. If you talk about two charges, each charge will exert some force on the other charge. It may be a attractive force or a repulsive force whose magnitude is given as k q1 q2 divided by r square, guys. K is proportionality constant, epsilon naught will be absolute permittivity or permittivity of free space, guys. Right now you see product of these two charges, point charges, if I take, if q1 q2 product is positive, means either both of them should be positive charge, both of them should be negative charge. So two like charges, what will they do, beta? They are going to repel each other. So whenever product of the charges is positive, usually if they are point charges, they will repel each other. If the product of the charges is negative, then it means one of them should be positive, other should be negative. It means they're unlike charges, guys. So they're going to attract each other. Always remember, electrostatic force will be a central force, guys. It is also a conservative force again, right? It is medium dependent, guys. It is medium dependent. So if you see, if the charges are surrounded by a medium, the net force experienced by the charge, what is happening? 1 by 4 pi epsilon it is becoming, guys, right? So this is the situation. This you can write, it is the situation in vacuum. So if two charges are placed in vacuum, 1 by 4 pi epsilon naught q1 q2 by r square, and if the charges are surrounded by a medium, guys, then the force will be, this is in medium again. Clear? Understood, all of you? So what we can write epsilon value as, it is permittivity of the medium. It can be given as permittivity of free space into absolute relative permittivity, guys. And this relative permittivity is also called as your dielectric constant. What is it called as? Dielectric constant. And as you can see, its value will lie between 1 and infinity. For metals, right, the value of k will be infinite, guys. It will be infinite again. Clear, all of you? Yes or no? And always remember, force between two charges will be independent of other charge present in the system. If I want to find force between Q1 and Q2, even if there is Q3, force between Q1 and Q2 will depend on only Q1 and Q2. It will not depend on Q3, guys. Is that clear, all of you? Right. What is electric field intensity again? So at any point, if you want to find basic thing again, I'm telling you, at any point you want to find field, force, potential, potential energy. Very simple logic. Field, force, potential, potential energy. It may be gravitational or electrostatic potential or electrostatic potential energy, or electric field, gravitational field, electric force, or gravitational force, guys. At any point, if they are asking us to find either of these four quantities at that particular point in electrostatics, I am going to place test charge. Test charge happens to be a unit positive charge plus 1 coulomb charge. Whereas in gravitation, at the given point, I am going to place a test mass. Test mass happens to be a unit mass, guys, 1 kg mass. So what is electric field intensity? In general, what is electric field, guys? It is space around a charge. Okay, it is space around a charge. Space around a charge will be called as its electric field. Space around a mass will be called as its gravitational field. So how do you find out the electric field intensity, guys? You will first find out force acting on the test charge at that particular point divided by test charge, guys. Very simple logic. Suppose if I have a positive charge q, I want to find field due to this charge at this point, guys. So this point is placed at a distance small r, let us consider. So I want to find electric field due to this particular charge. At which point? I want to find it at point P. So at whichever point you want to find field, force, potential or potential energy, at that point, what are we going to place a test charge? What will positive charge do to the test charge? What will it do it now? Is it going to repel or not? So this is the force acting or force experienced by the test charge. So what would be the magnitude of force experienced by the test charge? I can write it as K capital Q small q divided by R square. The magnitude of force experienced by test charge divided by test charge will be KQ divided by R square. So this will be the magnitude of electric field, guys. So it is electric field due to a point charge will be given as KQ divided by R square. Clear, all of you? Yes or no? Please remember, electric field will always be given as electric force experienced by the test charge divided by test charge itself. Clear? Electric force experienced by test charge divided by test charge itself. The units, if I consider, it is Newton per Coulomb. Which quantity it is, beta? It is a vector quantity again. Which quantity is it? It is vector quantity. If we talk about the dimensions of electric field, what will I get? ML. Again, Coulomb is anyhow A into T, guys. So you will get ML T power minus 3 A power minus 1 you are going to get. This will be dimensions of your electric field, which is vector quantity again. So as you can see, what did we get? Electric field due to a point charge. Just now we have done electric field due to a point charge. Did I again get it as KQ by R square? Yes. Now if you write it in vector form, guys, so electric field will be given as force experienced by test charge divided by the test charge only. So here I can write it as KQ by R square. Now is it acting in the direction of R bar or not? So from the given charge to the given point, this will be our R bar value. Because it is acting in the direction of R bar, I will write it as R cap. As it is positive charge, we will get the electric force in the direction of R bar. If it is negative charge, I am going to get the electric force opposite to the direction of R bar, guys. Clear, all of you? How do you find electric field? At any point, if you want to find field, force, potential energy, in gravitation, at that point, you are going to place a test mass. In electrostatics, at that point, you are going to place a test charge. Find the force experienced by the test charge divided by test charge in order to obtain the electric field intensity. Clear, all of you? Right. So we have already done electric field due to a point charge. So I'm not discussing that, guys, again. Now let us talk about neutral point. Very basic logic. So whenever we consider neutral point, it is that particular point where net gravitational force experienced by a test mass or net electric force experienced by a test charge or gravitational field at that point or electric field at that point should be zero. Clear, all of you? Neutral point or null point is that particular point where gravitational field, electric field, magnetic field are zero. Or we can say the gravitational force experienced by test mass kept at that point zero, right? Electrostatic force experienced by test charge placed at that point zero. Magnetic force experienced by test pole placed at that point will also be zero. So neutral point is that particular point where field intensity is zero. That field can be gravitational field, electric field or magnetic field, guys, right? So electric field intensity should be how much here? Electric field intensity should be zero. So those points where electric field strength is zero will be called as neutral point, guys. So as you can see, the different cases, two positive charges I have taken, right? So two positive charges we have taken which are at a distance 2r. They are like charges and they have same magnitude also, guys. And one more very important point I've forgotten to tell you. While we are writing the expression for electrostatic force, in the expression for electrostatic force, we will take only the magnitude of the charges. We are not going to take the polarity. Don't write if this is minus q1. Don't write 1 by 4 pi epsilon naught minus q1 q2 divided by r square. It is wrong. It is blunder, guys. Minus q1 is simply polarity. Negative is simply polarity of that charge. Positive is simply polarity of this charge. But in the expression for Coulomb's force or electrostatic force, we are going to take only magnitude of the charges, guys. What are we going to take? Only magnitude of the charges. If I write, the electrostatic force will be given as k into magnitude of q1, magnitude of q2, divided by r square. If it is a positive charge, plus r cap. If it is a negative charge, minus r cap. Okay, always remember, you are going to take only the magnitude of the charges. You are not going to consider the polarity while you are writing the expression for the Coulomb's law of electromagnetic force, guys, or electrostatic force, you can write here. Clear, all of you? As you can see, two like charges of same polarity and same magnitude are kept at some separation. Whenever two like charges of same magnitude and same polarity are kept at some separation, the null point will exactly lie at their midpoint, guys. They are going to lie where? At their midpoint. Same question again, if I take here, we have negative charge, here we have negative charge. Let us take this is minus q charge, this is also minus q charge. Right, so as you can see, these are identical charges. Yes, they have same magnitude as well as same polarity, guys. So where will the null point lie? Exactly at their center. So if this is your r distance, this will also be r distance, guys. Clear, all of you? In the same manner, if we don't have, right, if I don't have identical charges, right, they may be either like charges, they may be unlike charges. Let us imagine they are separated by some distance r, guys. Okay, and I have some charge q1 and q2. Okay, we have some charges q1 as well as q2. They're asking for this set of charges, where is null point? Assume q1 and q2 are positive charges, guys. So I will also consider, right, this point to be some null point, guys. I'm imagining that point P is null point and it is at a distance x from q1. So at any point, if I want to find field, force, potential, energy, at that point, firstly, I'm going to place a test charge. Test charge will always be a unit positive charge plus 1 coulomb charge, guys. Now, please tell me, what will q1 do to positive charge? Point charges, no? So definitely it will be repelling. This is force on 1. What will q2 do to this charge? Again, it will also repel, guys. It is force due to 2. Now, for p to be null point, for p to be what? For p to be null point, what will we consider for p to be null point? What is the condition, guys? The net force at that point should be how much? 0. Now, at this point, you have two forces. When will net force be 0? They're already opposite in direction. So net force will be 0 if their magnitudes are same, guys. So what I can write between q1 and q, what is the magnitude? K into q1 small q divided by x square. Between q and q2, what is the magnitude of the force beta? K into q2 into q divided by r minus x whole square, guys. So from this, if you just solve for this value, you are going to get x is the distance from q1 charge, guys. So what are we going to get x value as? I'm going to get it as r divided by root over q2 divided by q1 plus 1 if you have like charges. If you have unlike charges, guys, in denominator you will write minus 1 again, because for like charges neutral point will be lying between them. For unlike charges, either it will lie to the left of q1 or it will lie to the right of q2, guys. Clear, all of you? Yes or no? These are not A2 and A1, these are Q2 and Q1, guys. So this is the distance from which charge? This is from which charge? X is the distance from Q1 charge. In the same manner, you will have masses in gravitation, and the answer will be R divided by root over M2 by M1 plus 1, guys. As simple as that. So it's a very important formula again. R divided by under root of, it is q2 by q1, guys, plus or minus 1. Plus will be used for like charges because neutral point will be lying between them, and minus will be used for unlike charges because neutral point will lie outside them. What do I mean by outside them? Either to the left of q1 or to the right of q2. And very important point, third point, if you see, guys, again it is valid in case of gravitation also. If you take a regular geometrical shaped object, what are we taking? We are taking a regular geometrical shaped object and we are placing identical charges on the vertices, guys. See, you can take equilateral triangle, right? Not only equilateral triangle, guys. I can take a square also. I can take a regular pentagon. I can take a regular hexagon. I want to take any regular shape. You can take regular shape, guys. And what we are going to place on the vertices, I am going to place identical charges again. Let us say all negative charges I have placed here. Then in this case, what is going to happen? Whenever identical charges are placed on the vertices of a regular polygon, then in such case, the electric force, electric field at their center will be 0. So the center, their geometrical center will be the null point, guys. So here, this you can consider will be our null point. So always remember, if you take a regular geometrical shaped object, right? For regular, not a rectangle again. You should take a polygon whose all sides are equal. Polygon whose all sides are equal is called as a regular polygon, guys. Okay, so what are we going to take? If you take a regular geometrical shaped object, identical charges, very important condition, identical charges are placed on the vertices of that particular polygon, then what will happen? The null point will lie at their geometrical center. It means the resultant electrostatic force or the field at point O will be 0. Is that clear? Is that clear, all of you?
Yes, sir.
Yes.
Let us talk about electric lines of forces, guys. When we talk about electric lines of forces, so basically these are imaginary lines around the charge, guys. And at any point, if you want to find direction of electric field, you are just going to draw tangent at that particular point. What are electric lines? These are some imaginary lines or curves surrounding a charge. And at any point, if you want to find the direction of electric field, at that point, you are simply going to draw a tangent, guys. So as we can see, the electric lines of forces are which lines, beta? They are imaginary lines or curves, right? So what they are saying is, if they are straight, obviously, if they are straight means, let us say they are represented by an arrow mark. If electric field lines are straight, if they are represented by an arrow mark, then that only will be the direction of electric field. If they are curved, guys, very important again, if they are curved, how will you find? You will draw tangent drawn at that point will give us the direction of electric field. Clear, all of you? And always remember, the strength of the charge will determine how many number of field lines are going to come out from the charge or they are going to enter that charge. Usually from positive charge, electric field lines will come out, guys. Into negative charge, electric field lines are going to end, or at negative charge, they are going to terminate or end, guys. How many field lines are associated with the charge will depend basically on strength of the charge, guys. So you can see number of field lines crossing a cross section is proportional to the strength of the electric field. More number of electric field lines, more will be the strength of the electric field, means more will be the strength of the charge also, guys. Clear? Is that clear, all of you? The number of field lines will always depend on, if we talk about number of field lines, number of field lines will directly be proportional to magnitude of the charge, guys. So more number of field lines are associated with a charge means more is the strength of that particular charge, more will be the strength of the electric field produced by that charge, guys. So as you can see, for a point charge, isolated point, very important, guys. Isolated means it is separate, just like me, huh? It is isolated from the surroundings, guys. So I am isolated from the surroundings. Isolated means no surroundings effect will be considered on the system. So for an isolated point charge, if it is positive charge, for positive charge, electric field lines will be radially outward. For negative charge, they are going to be radially inward. So for an isolated positive charge, guys, the electric field lines will be radially outward. For a isolated negative charge, guys, electric field lines will be radially inwards. Okay. And we also have something called as electric dipole. What basically is electric dipole, guys? It is a set of two charges which are equal in magnitude, opposite in direction, kept at some separation. When two charges equal in magnitude, opposite in direction are kept at some separation, it is going to form a dipole, guys. So please understand, right? So in this situation, you have negative charge, you have positive charge, right? Are they alone? No. If they were alone, the electric field lines at negative charge, how it would have been? Radially inward. If positive charge was alone, it would have been radially outward. But because they are placed in such a way that they are influencing each other, guys. So this would be the electric line diagram or electric force diagram for electric dipole, guys. Always remember, from positive charges, electric field lines are going to come out, right? At a negative charge, electric field lines are going to enter. So if electric field lines are entering, let us say, then in that case, that charge will be negative. If electric field lines are coming out of a point, let us say, then that point will have a positive charge. Clear, everyone? Yes or no? So this would be the electric lines force diagram for a dipole. In the same manner, for identical charge, you can take it something in this manner. Okay. These are electric field lines diagram again. Okay. Clear, all of you? Is that clear, everyone?
Yes, sir.
Right. Now, please tell me, if you take negative charge, how many field lines are associated with it, guys? Count the number of field lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 field lines are associated with this charge or not? Let us imagine this is Q1, guys. How many field lines are associated with positive charge, you see? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 only are associated again. So they will ask you what is the ratio of their strength. So what I can say, magnitude of Q1 divided by magnitude of Q2. What will it be? With Q1, how many field lines? 10. With Q2 also, how many field lines? 10. So what will they be? The charges magnitudes will be same. Clear, all of you? But I can say, by looking at this, from Q2 charge, field lines are coming out. So I can come to a conclusion that Q2 charge will be a positive charge. At Q1 charge, field lines are entering. So I can say that Q1 will be negative charge, guys. Is that clear, all of you? Right. Some properties of electric lines of forces, if you see, as I have said before just now, right, they are going to come out of positive charge. They originate from positive charge, guys, and they are going to end at or terminate at negative charge, guys. Similarly, always remember, electric lines are continuous curves. What are they? They are continuous curves, guys. They are not going to break anywhere. I'll break, then I'll continue here, then I'll break, then I'll continue here. No, they're always continuous curves, but they are not closed, guys, right? You have two types of electric field. One, in electromagnetic induction we study induced electric field, guys. Induced electric field can form closed loops, guys. However, generally if you take electric field, it is conservative in nature and it is not going to form closed loops again. Clear? So in free space, the electric lines of forces, they are continuous curves. They are not going to have any sudden break, guys. And can two field lines intersect? No, again, two field lines do not intersect. Why they do not intersect? Very basic thing. You have two directions of electric field at a point, which is not possible at all. They contract longitudinally, it seems, right? Contracting longitudinally means initially they are far away, let us say. As they move towards each other, they are going to, again, as they move some horizontal distance, they will come closer to each other, guys. And they are going to exert some lateral pressure, right? And on account of repulsion between the charges. So it's not that much necessary, but I think once you have been asked this particular point, guys, so it is important again. So they are going to exert lateral pressure on each other. Now please tell me, why are these not possible? First one, why is it not possible?
So because it is passing through the charge.
हाँ, तो पासिंग थ्रू चार्ज नहीं हो सकता क्या?
So point charge.
पॉइंट चार्ज, अच्छा, तो पास नहीं हो सकता क्या? किसने कहा? मैंने कहा
Positive charge.
It cannot
हाँ,
intersect.
it cannot intersect. अच्छा, it is not intersecting
Positive.
anyway. There are four different lines, you see. It is positive charge, guys. From positive charge will electric field line C. Can electric field line enter into positive charge? Can it enter? This field line, if you see, it is entering into positive charge. Is that correct? No. This field line also, you see, it is entering into positive charge. Into which charges will they enter, guys? Into negative charges. So this will be wrong. However, these two may be correct, guys. This is one field line, this is one field line, which are coming out of the positive charge. So these two may be correct, but the other two lines are wrong. So this will be a wrong pattern. Second thing, second, why is it wrong? Second, why is it wrong?
So closed and
Loop,
closed.
closed loop.
It cannot form closed loop again. So in second case, it is forming closed loop, guys. So it will be wrong again. Is that clear, all of you? Yes or no? However, if I am saying a statement, electric field lines can form closed loops, will that be correct statement?
Yes.
Yes. Which type of electric field lines, guys? Induced electric field lines can form closed loops. So whenever a statement is asked electric field lines can form closed loops, it is correct if I take only conservative field produced by a charge, right? That will be conservative field produced by a changing magnetic field will be your induced electric field, so that will not be conservative. Third one, why is it wrong?
It's the intersection.
They are
Intersection.
intersecting, that is the reason there it is wrong. Fourth one, guys, again it may be correct to some extent, but as you can see here, right, they are not contracting longitudinally. As we move ahead from one charge to other charge, they usually contract. However, I can say this is correct. This will be correct for a non-uniform field, guys. Which type of field we are talking about? Non-uniform field. So they are not contracting. So as they move, so what they have given, they contract longitudinally on account of attraction between opposite charges. So in fourth case, there may not be a contraction. That is the reason fourth one will be wrong. Although I cannot say that it is definitely wrong, guys. It may be possible for a non-uniform field also. Okay. Clear, all of you? Now we have electric dipole. What basically is electric dipole? As I have said in general just now, what is electric dipole, guys? Whenever we have two charges of equal magnitude and opposite polarity kept at some separation, then that system is going to behave as a electric dipole. So two equal and opposite charges separated by some distance will behave as an electric dipole. And whenever we talk about an electric dipole directed from negative charge towards positive charge, we are going to have a quantity called as electric dipole moment. It will always be directed from negative charge to positive charge. Same thing you will get in magnetism also. Magnetic dipole moment. It will be directed from south pole to north pole, guys. And what will be the magnitude of this dipole moment? As you can see, magnitude of the dipole moment will be given as magnitude of one charge, any charge you may take, magnitude of charge into separation between them. It will be given as magnitude of charge into separation between them. It is very important again, right? It will always be directed from negative charge to positive charge. So SI unit will be coulomb meter again. Now, what is the meaning of ideal dipole, guys? Ideal dipole can be considered as a short dipole also. Large magnitude of charges, small separation will be considered as a ideal dipole or short dipole. So I will represent ideal dipole just by a small line, guys, and arrow mark will give us the direction of electric dipole moment again. Clear, all of you? Yes or no? All these are not required. Debye and all, Debye CGS unit of dipole moment, right? Coulomb meter is SI unit, so those are not that much essential, guys. Now electric field due to a dipole is very important, so they have not given. Let us talk about electric field due to an electric dipole, guys. Now, as you can see here, we have negative charge and positive charge. Okay, whichever a line passing through the charges as well as their midpoint will be the axis of the dipole, and any point on the axis will be called as the axial point. In the same manner, a line passing through the center, not through charges, perpendicular to the charges or perpendicular to the line joining the charges, this will be your equatorial axis. Any point on the equatorial axis will be called as equatorial point, guys. So please do remember, I'm not proving the formulas here, guys, right? So what would be at electric field at axial point? It will be 2 p bar into r divided by 4 pi epsilon naught r square minus a square whole square. For short dipole, 2 p bar divided by 4 pi epsilon naught r cube, or in general what we can write here, we can write 2k p bar r square minus a square whole square, and I can write this as 2k p bar divided by r cube, guys. Okay, this is electric field due to a dipole at an axial point. This is for normal dipole, this is for a short dipole. Always remember, at an axial point, electric field at axial point, what is it, beta? It is parallel to, it will be in the direction of dipole moment. In the same manner, electric field at equatorial point, guys, right, it will be parallel to minus p bar. It is opposite to the direction of dipole moment. Dipole moment will always be directed from negative charge to a positive charge. And as you can see, right, please understand, a line passing through the charges and their common center will be called as axis of the dipole. Any point on the dipole can be considered as the axial point. Likewise, Any line passing through their center and perpendicular to the line passing through the charges will be called as equatorial line, and any point on equatorial line will be called as equatorial point, guys. So what would be electric field at equatorial point? It's very basic again. At equatorial point, it is written as k into minus p bar divided by r square plus a square whole power 3 by 2, guys. Right, this is due to a normal dipole again. This is normal dipole axial point. Okay. This is normal dipole, sorry, short dipole axial point. This is normal dipole equatorial point, k minus p bar divided by r square plus a square whole power 3 by 2. In the same manner, due to a short dipole, I can directly write it will be k into minus p bar divided by r cube, guys. Okay, this will be due to short dipole at an equatorial point. So please remember, for an ideal dipole or short dipole, as you can see here, it is 2k p bar by r cube. Here it is k p bar by r cube only. So what we can tell, what we can come to a conclusion, electric field at axial point will be minus of 2 times the electric field at equatorial point, guys. Electric field at axial point will be minus 2 times of electric field at equatorial point. If I write only magnitude, you can say directly electric field at axial point will be 2 times the electric field at equatorial point. It is very important case again, okay, because this concept will be utilized in proving the electric field at radial point, guys. What is radial point? That particular point which is neither lying on the axis of the dipole nor on the equatorial axis. Such point will be called as a radial point, guys. Clear, all of you? Yes or no? Right. So as you can see, in case of a radial point, what will be electric field? We will be focusing majorly on magnitude only, guys. The magnitude of electric field at axial point, if I take radial point, if I take, you will get it as kp by r cube under root of 1 plus 3 cos square theta. Now as you can see, how we will prove is, if again at radial point we can do only for a short dipole, we cannot do it for a normal dipole, guys. So if you take a short dipole means a small vector you are going to place at origin, it will behave as a short dipole. And what is this point? Point P happens to be radial point. So I want to find at radial point. What are we going to do? We are going to resolve this electric dipole moment into two components. One I will get P cos theta, other I will get P sin theta. For P cos theta dipole, so now I got two dipoles, guys. For P cos theta dipole, the given point will be an axial point. For P sin theta dipole, the given point will be a equatorial point. So for P cos theta, you will get electric field in the same direction. For P sin theta dipole, you will get electric field exactly in the opposite direction, guys. So alpha value also you can see, alpha value will be given as tan inverse of half tan theta, guys. So what is angle between dipole moment? Dipole moment is along x-axis, right? Electric field is something like this, net electric field. So net electric field is kp by r cube under root of 1 plus 3 cos square theta. It is making an angle alpha with p cos theta component, guys, or it is making an angle theta plus alpha with x-axis. So if electric field becomes perpendicular to p bar, very important case again. When electric field becomes perpendicular to p bar, it means theta plus alpha will be 90. Theta value will be tan inverse of root 2. I will just add some more points here. Alpha value will be tan inverse of 1 by root 2. Or you can say alpha value is cot inverse of root 2. Theta value will be cot inverse of 1 by root 2. Is that clear? Again, please remember these values. For short dipole at axial point, 2k p bar by r cube. For short dipole at equatorial point, k minus p bar by r cube. At radial point, you can define only due to a short dipole, which is kp by r cube into under root of 1 plus 3 cos square theta. Angle between electric field at radial point and given dipole moment will be theta plus alpha. If electric field at the radial point and dipole moment are perpendicular to each other, theta plus alpha will be equal to 90 degrees. Theta value will get it as tan inverse of root 2. Alpha value will get it as tan inverse of 1 by root 2. These points you should remember in case of calculation of electric field due to a dipole, right? At axial point, equatorial point, at any radial point, guys. Clear, all of you? Yes or no, yaar?
So could you explain the relation of conservation and it not forming a circular field?
क्या
So could you explain the relation of why is it not forming a circular field because of conservation?
property of it here, it is not going to form again. If it forms if it forms a circle again, right, it should be originating from a point source, let us say. So from a point source, if it is originating, right, and we already got to know that from point source it is radially outward. Yes or no? Basically, if I create a disturbance, just like if you take still water, you are dropping a stone on it, what will happen? You will see the ripples which will be projecting out. In which manner? What exactly I'm saying is, see, suppose if I take positive, and very easily I'll explain. Okay, I'll take 2 points. What I'll do, I'll take 2 points on them. Very simple. 2 points I'm taking. Here. Is there any charge?
Sorry, sir.
Is there any charge?
Sir, which point?
Both are same points only I'm saying, but just for understanding purpose, I'm keeping it separate. Is the pointer visible?
Yes, sir, it is.
So here I'm taking positive charge. So is a charge coming, is a electric field line coming out of this charge?
Yes, sir.
And here negative charge we have taken. Is the electric field entering into that charge?
Yes, sir.
But overall in reality, is there any charge?
No, sir.
No. So charge is not there. What is the reason for electric? What is electric field? It is space around the charge. So here both positive and negative charge is there. Same in magnitude again, because one field line only is there. So how much is the net charge here?
0.
0. So should there be any field line?
No.
But there is field line, no?
Yes.
So that is the reason this cannot happen. Clear?
Okay. Yes.
Right. Similarly, whenever a dipole is placed in a uniform electric field, how do we understand or visualize uniform field? I'm not only saying uniform electric field, it is applicable for uniform magnetic field, it is applicable for uniform gravitational field also. Whenever we have equispaced unidirectional field lines, such type of field will be a uniform field. Either it can be a electric field, magnetic field, or gravitational field. So two cases will be arising, three cases are there, four cases are there in reality again. So whenever P bar is parallel to E bar, first case. So P bar is parallel to E bar means there is no angle between them. Theta value will be how much here? 0. So net force, as you can see, it will be 0 only. No torque against stable equilibrium. Stable equilibrium means potential energy is what, beta? Potential energy is minimum here. When they both are anti-parallel to each other. So in this case, what is theta value? First case, theta value is 0 degrees. In second case, theta value will be what, beta? 180 degrees. In this case also, net force is 0. Net torque 0, but it will be in unstable equilibrium. In this situation, potential energy experienced with the dipole is maximum, guys. Okay. Third case, if you look at when P bar is perpendicular to E bar, if I take P bar is perpendicular to E bar, in this case, what is angle between them, beta? 90 degrees. So will there be any force? No. Torque will be there? Yes, torque will be there, which is maximum. So always remember, they will ask you the ratio of maximum torque to maximum energy, potential energy, something like that they may ask. So maximum torque will be given as how much, beta? P into E. In general, torque experienced by a dipole placed in a uniform field will be P bar cross E bar, which I can write it as P E sine theta n cap. Clear? This is in general torque. Again, maximum potential energy if I take, you will write it as plus PE beta. Okay. And in general, potential energy will be given as minus of P bar dot E bar, which I can write it as minus PE cos theta. So in the third case, angle between them is how much? 90 degrees. So that is the reason maximum torque will be experienced, and this will be in, again, why, what is given? Translation equilibrium, but not in rotational. Okay, you keep this aside. It will be in neutral equilibrium, guys. In this case, although it is, again, in every case, here torque is 0, force is 0. So in first case, both translation as well as rotational equilibrium. In second case, torque is 0, force is 0. So rotational as well as translation equilibrium. In third case, Force is zero, rotational equilibrium. Torque is not zero, so it is not in rotational equilibrium, guys. Similarly, it will go with fourth case also. So always remember, whenever a dipole is placed in a uniform electric field, it will never experience force. But if it is placed in a non-uniform electric field, it will always experience force. Clear, all of you? It will always experience force if it is placed in a non-uniform electric field. If it is placed in a uniform electric field, it will never experience force. Uniform electric field may or may not experience torque. Non-uniform electric field also may or may not experience torque. Okay, so whenever I take a dipole placed in a uniform electric field, I will say it will always be in translational equilibrium, may or may not be in rotational equilibrium. If I take a dipole and place it in non-uniform field, it will never be in translational equilibrium, may or may not be in rotational equilibrium. Is that clear? Is that clear? So in the fourth case also, as you can see, P bar is making a certain angle theta with E bar. That theta can be any arbitrary value. It can be 0, 90, 180, guys. So it is going to experience some torque given by Pe sine theta. It is not going to experience any force, guys. Clear, all of you? You understand or not, everyone? Uniform field is there. Dipole, if you take an electric dipole, where is it placed? In uniform electric field. Dipole placed in uniform electric field. Force what, beta? Force experienced? Always zero. Force always zero means it will definitely be in translation equilibrium. Torque, beta, may or may not be zero. So it may or may not be in rotational equilibrium. In the same manner, if you take an electric dipole, same goes with bar magnet also. Okay, if you take an electric dipole, if it is placed in non-uniform field, if it is placed in what, beta? Non-uniform electric field, right? Will it experience force? Force never zero. Means it will always experience force. Torque again may or may not be zero, guys. Torque may or may not be zero. Clear, all of you? Torque may or may not be zero. Force always zero. Torque may or may not be zero in uniform electric field. If it is placed in non-uniform electric field, force always zero. Sorry, force never zero. Torque may or may not be zero. Is that clear? Understood, all of you? Right. So as I've already written just now, potential energy experienced by dipole if it is placed in a uniform electric field will be minus P bar dot E bar. Also remember, guys, again, as I am saying that it is experiencing a force. Did I say it is experiencing force if it is placed in non-uniform field? Yes, I am saying that it is experiencing force, guys. Right. So what would be the force experienced again if we talk about? So potential energy we got minus P. Yes or no? So if I write force experienced, beta, it will be given as magnitude only. I'm writing. It will be given as P into dE divided by dr. It's a very, very important case again. This is the force experienced by a dipole placed in a non-uniform field. P into dE divided by dr. So if you solve for this, guys, force of interaction between dipoles, they will ask you. The force of interaction between dipoles will be inversely proportional to r power 4. If you solve for this, you will get that again. Okay. The force of interaction between dipoles. Force of interaction between dipoles. If you take it, guys, you will get it as inversely proportional to r power 4. If they are kept at a distance r apart, then force of interaction between them will be 1 by r power 4, guys. Clear, all of you? And they will ask you what will be the work done in rotating the dipole. So while you are rotating the dipole, no, you have to rotate it against the torque. So as you are rotating against the torque, work should be done by external agent, guys. So always remember, work done by external agent. What will be work done by external agent? It will be change in potential energy. Change will always be final minus initial. What I'll get this as? I'll get it as PE into cos theta initial minus cos theta final. I'll get. Okay, so they will ask you what is the work done to shift its position from some angular position theta 1 to angular position theta 2. So while you are shifting the position, you have to do some work against the torque. Work done against the torque will be work done by external agent, and you all know work done by external agent will be written as change in potential energy, PE cos theta initial minus cos theta final. Is that clear, all of you? Then next we have something called as electric flux. What in general is electric flux again? So flux is simply how many number of electric field lines or magnetic field lines or gravitational field lines are crossing per unit area. That will be called as your electric flux. So as you can see, what are they basically? These are number of field lines that pass through a surface. Again, number of field lines passing per surface and normal to it, we basically write it as. In case of axially and equatorially placed dipoles, what would be interaction force? Same, it will also be inversely proportional to r power 4 only. Okay, I'll just tell you this. Axially and equatorially means one is like this, yes or no? Other would be something in this manner. Clear? That is what you're asking.
Yes, sir.
Now, what is the situation in this? You see, both are short dipoles only. Okay, both are short dipoles only. This is equatorially placed. Now, let us say this is first dipole, this is second dipole. I'm just proving it. It is also inversely proportional to r power 4 only. For first dipole, this point happens to be which point? For first dipole, this point happens to be equatorial point. So how will electric field be? It is going to be in this manner or not? Let us say the distance between them is r. So what will I get here? I'm going to get it as Kp1, let us say, divided by only magnitude I'm talking about, Kp1 divided by r cube. This is the electric field again. Now you see, I have a dipole moment P2 you can consider. Electric field is like this. What is angle between electric field and dipole moment now? Is it perpendicular or not? P bar and D bar, will it be perpendicular? Yes, it is perpendicular. So what you're asking force experienced because it is varying again. So what will I get? Force as, I'm going to get it as P into P2 into dE1 due to first dipole divided by dr. So again you take P2 d by dr of, you can write it as Kp1 divided by r cube. So I'll get it as Kp1 P2 will be constant and d by dr of r power minus 3 you will get, which will be proportional to r power minus 4, which will be inversely proportional to r power 4. Clear? Understood? Is that clear? Harshit, is it clear? If the point is defined, then you can say it is constant value, it is not going to experience any force if the point is defined. But certainly r is keep going on changing, r will change again. So as smaller value, it can be anywhere precisely. So as smaller value keeps on changing, you can say force keeps on changing. Okay. Let us talk about flux, guys. So what is flux basically given as? Number of field lines passing per unit area and normal through the surface. That will be called as the electric flux, guys. So as you can see, if you have uniform field, for uniform electric field, flux will be given as dot product of electric field and area vector. So which quantity is going to be beta? Because it is dot product, it will be which quantity? Scalar quantity. And as you can see, units will be Newton meter square per coulomb. Dimensions are very important again, guys. So what will I get? I'll get it as ml cube t minus 1. This would be the dimensions because Newton is ml t power minus 2, ml cube t power minus 2. If I send this in the numerator, again I'll get ml cube t power minus 3 a power minus 1. This would be dimensions of electric flux. For uniform field, directly dot product, guys. For non-uniform field, you need to perform integration. Integral E bar dot dA bar. This is for which type of field? This is for non-uniform field. If you have uniform field, directly I'll write it as dot product again. Right? So I can write it as EA cos theta also. And what will be, because it is obtained by performing dot product of two quantities is scalar quantity, dimensions will be ml cube t power minus 3 a power minus 1. Clear all of you? In first case, you see, in all the cases, let us imagine the field is uniform electric field. How is the electric field? Is uniform. In all the cases, let us imagine electric field is uniform, guys. Right? So for uniform field, what we can write? for uniform electric field, I can write the value of electric flux as E into A into cos theta. And what is theta, beta? Theta in general is the angle between electric field vector and area vector. And always remember, if there is any surface, right, if you take any object, it has some surface, yes or no, area vector will always be perpendicular to that surface, guys, and usually perpendicularly outwards it is going to be. How will it be? It will be perpendicularly outwards again. So if I take this particular situation, as you can see, electric field and area vector both are in same direction. So here in first case, theta value will be 0 degrees. So what will be the flux associated? E into A. In second case, area, so I am considering a disk placed on floor. So what will area vector be? Floor means horizontal plane, so area vector will be along y axis, guys. In first case, electric field is also along y axis, where, so what will theta value be here, beta? Theta value will be 90 degrees. In third case, it is making a certain angle theta with a bar. So in second case, because theta is 90, cos 90 will be 0, so flux will be 0. In third case, you can consider it will be due to E cos theta electric field. Due to E sin theta, you will not get. So you will write E A cos theta again. Now, always remember, guys, whenever we talk about flux, we should consider projected areas. What is the meaning of projected areas? You take a sphere, you place it very far away from us, guys. How will it appear? Will it appear like sphere? Moon you take, in reality it may be spherical in shape, but because it is very far, how will it appear to us? As a circle again, yes or no? So it is a projected area. You take a cone, place it upright, keep it very far, will you be able to see three-dimensional space? No, you will be able to see a triangle, guys. If you place a cone opening surface like this, guys, right, you place it very far, it will appear to be like a circle again. Right, so there are different cases again, guys. You take a cuboid, place it very far, it will appear just like a rectangle again, right? So in this case also, as you can see, right, so there are two surfaces here. One will be, and one more very important point is, whenever we take a uniform field and a closed object, if a closed object is placed in a uniform field, the total flux associated with that particular closed surface will be 0. So if you take cone, it is also a solid cone again, so you can consider it to be a closed surface, and it is placed in uniform electric field, guys. So because it is placed in uniform electric field, total flux associated with the whole cone, I'll consider it as 0. Now for base, see, base is like this, guys. This is the base. Imagine if it is visible, this is the base, circular form. So how will area vector be? Area vector will be perpendicularly outwards like this. If you can just see this, if you are able to see this, it is in the circular form. So how will area vector be? It is perpendicularly outward, guys. Perpendicularly outward. So for this particular part, how will area vector be? Outward. This is our area vector. Electric field is also in the same direction. So if I am interested in finding flux through base, guys, what will it be? Electric field and area vector both will be in same direction. So I'll write E A cos 0. So I can write it as E into pi r square. Cos 0 is anyhow 1. Through the entire cone, it will be 0. It has two surfaces. One is base, other is curved surface. So what will be curved surface, beta? It will be, because total flux has to be made 0, for curved surface it will be minus into pi E into pi r square. Clear, all of you? Understood, everyone? Whenever you are taking a closed surface and placing it in a uniform electric field, net flux associated with it is 0. Here I have two surfaces. One is the curved surface, other is the base surface. So I have calculated for base, guys. For base, I got E into pi r square. In order to make the entire flux 0, what will it be through the curved surface, guys? It will be minus E into pi into r square. Clear, all of you? In the same manner, sphere also you see, right? They have taken a hemisphere. Hemisphere they have taken, guys. So below surface will again be in the form of, circle. So area vector will be downwards for this surface, guys. I'm talking about this surface. For this surface, area vector is, where is it going to be? Downward. but electric field is along positive x direction. So what is the flux through base in this case? Flux through base, can you tell? Area vector, if there is any surface, area vector will be perpendicular to the surface, guys. So surface is base here, it is placed in xz plane and it will be usually perpendicularly outward, guys. So what will I get? E into A into what is angle between them? Cos 90 again. So flux through the base will be how much here? 0. Flux through the curved surface, entirely it will be 0. So because total flux should be 0, no? Two surfaces it has. One is base, other is curved. Because it is a closed surface placed in uniform electric field, total flux should be 0. So for base it is 0 means obviously for curved surface also it should be how much beta? 0. So inward flux and outward flux both will be equal. Inward flux will be negative, outward flux will be positive. You can use that. Clear all of you? Yes or no? Right, same thing. In this also they have given you sphere, hemisphere only, but it is placed vertically. In the previous case, hemisphere was placed horizontally, guys. Now it has been placed vertically. Again, you have two surfaces. Now, if you talk about this surface, base surface I'm taking, guys. It is placed in YZ plane. So area vector will be along negative x-axis. But electric field is along positive x-axis. So if I again take for base, what will I get? I'll get it as E into A into cos how much beta? 180. So I can write E into pi r square cos 180, you know it is minus 1. So through base it will be E into pi r square negative. Totally it will be 0. So automatically what should it be through curved surface beta? It should be, in order to make it 0, it should be plus E into pi r square. Clear all of you? Understood or not? Flux through a closed surface placed in a uniform electric field should be 0. Similarly, flux through a bar magnet placed in a uniform magnetic field will also be 0, guys. Clear all of you? Understood flux calculation? For uniform electric field, directly you write E bar dot A bar dot product. For non-uniform electric field, you have to make use of integration. And very important point is, if you are taking a closed surface and placing it in a uniform field, guys, total flux associated with the surface should be 0. It means flux through all the surfaces, if you add, it should be 0. Okay. Next, Gauss law is important. What is Gauss law stating? Right, Gauss law in electrostatics it is also one of the, or I can say first of Maxwell equations, guys. So what is he stating? The flux associated with a closed surface, guys. It will be given as, just now we found it is integral E bar dot dA bar, but it will be given as Q enclosed divided by epsilon naught. Very important, right? Now, electric field is there. What is this electric field? This electric field should be due to all charges present in system, guys. Should be due to all charges present in system. In Gauss law, integral E bar dot dA bar is used as Q enclosed divided by epsilon naught. Electric field on left hand side should be due to all the charges present in the system, whereas Q enclosed on the right hand side should be only charges present inside the Gaussian surface. Charges present inside the Gaussian surface. Now, what are those charges, guys, or what is a Gaussian surface? They are simply special spherical surfaces. What are Gaussian surfaces? They are some special spherical surfaces. So what is Gauss law stating? Flux through a closed surface placed in electric field will be given as integral E bar dot dA bar, which is Q enclosed divided by epsilon naught. Q enclosed should be only those charges that are present inside the Gaussian surface. Electric field should be due to all the charges that are present in the system. Is that clear? Yes or no? So different cases are there. Now, as you can see, cube you have taken. You are placing the charge at the body center, guys. When you are placing the charge at the body center, what is the flux associated to the entire cube? Q by epsilon naught. And what will be flux through each phase? This totally will get divided in all the phases. Because you have 6 phases. Through each phase, it will be Q divided by 6 epsilon naught. Clear all of you? Now you see, right? It is placed at one of the corner. So whenever it is placed at one of the corner, guys, right? In this case, only 1/8 of the charge will be inside this cube. Because 1/8 of the charge is inside, the flux will be q by 8 epsilon naught. And this charge, I'm just drawing it over here, guys. This charge will be present in three phases. It will be present in this phase. Is it present in this phase or not? Yes, it is present. It will also be present in this phase. And it will also be present in this phase, guys. Uh, A, B, F, E. So in whichever phase that particular charge is associated, through those phases, the flux will be zero. So flux through three phases will be zero, and through other three phases, the total flux will now get divided in the other three phases. So it should get equally divided. So what I'll get? Q by 24 epsilon naught for those phases which are not containing the charge. For those phases which are consisting the charge, guys, what would be the total electric flux? It will be zero. Now, when it is placed at phase center, first is body center, second is corner, third is face center. When it is placed at face center, guys, now please see, only half of the charge will be associated with the cube. So I'll get q by 2 epsilon naught. Now, how many faces are containing this charge, beta? How many faces are containing the charge? Only one phase is
One.
containing the charge or not? So through this phase, the flux will be zero. And the total flux will now get equally divided in the other phases, guys. So flux through each other phase can be written as q divided by, this will get divided into 5 equal again. So q by 10 epsilon naught we can write. Clear all of you? The next one is placed at edge center, as you can see. When it is placed at edge center, with each cube you will have only 1/4 of the charge, guys. So that is the reason, as you can see, only 1/4 of the charge is there. So flux through the cube will be q by 4 epsilon naught. Likewise, in how many phases is this charge present? With how many phases will this charge be present? As you can see, it is present in this phase, yes or no? And it will also be present in this phase, beta. So with how many phases is it present? With two phases it is present. So what would be flux through these two phases? Zero. So this will get divided equally into four other phases. So what I'll get? Q by 16 epsilon naught I'm going to get. Clear all of you? Now these things, the electric field of different objects, these are derived from Gauss laws. I have not taken the derivation out of it, but you should please remember all these cases, guys. Whenever we talk about a point charge, the field will be given as kq by r square. If you take a shell, guys, on shell, mass will be present only on the surface in a shell. So charge also will be present only on the surface. Inside you are not going to have any charge. So that is the reason inside it will be zero, outside it will be same as that of point charge. For a uniformly distributed non-conducting solid sphere means the whole mass and charge will be distributed in its volume. So outside it will be same as that of point charge, guys, kq by r square, but inside it will be kq by capital R cube into small r. Please remember, inside it will vary as directly proportional to r, outside it will be varying as inversely proportional to r square. This will anyhow be inversely proportional to r square. This also outside inversely proportional to r square. Right? If you take a line charge if we consider, guys, for line charge it will be given as lambda divided by 2 pi epsilon naught r. So here also if you see, it is inversely proportional to r, and lambda will be your linear charge density. Line charge means charge will be distributed in length. Whenever charge is distributed in length, we will talk about a quantity called as linear charge density. So I'll get lambda divided by 2 pi epsilon naught r. R will be the perpendicular distance from the line charge, guys. Similarly, for a plain sheet of charge, if it is non-conducting, it will be given as sigma by 2 epsilon naught. For a conducting sheet or a conducting plate, if I take, you will get sigma by epsilon naught. So these are the values that you should remember. Clear all of you? Now, if you look at first the case of electric flux, they're asking if a charge, very important case again, if a charge is placed at a height a by 2 from the surface of one of the face, what is the flux associated with this surface they're asking. So what I'll do is I will simply close that charge from all sides. What we are going to do, beta? We are going to simply close this charge from all sides. So now, will it again be a case of charge placed at body center or not? And the given phase, if you look at it, guys, the given phase, does it happen to be one of the phase? Charge is placed at body center. So flux associated with the entire cube will be q by epsilon naught. And what would be the flux associated with the given phase? It is one of the phase, no? So q by 6 epsilon naught will be. Directly you will get these questions again, guys. Clear, all of you? That clear, everyone?
Yes, sir.
Usually you can expect questions from Coulomb's law, basic questions if you are getting, or you may expect questions from dipole, right? Or you may expect questions from the variation of electric field and electric potential for different objects, guys, for different charged objects. Did you understand, all of you? Again, however, problems discussion is key area. Formulas, so anyhow you should know, and basic properties you should know. Any doubt in charges and fields? Yes, no? All of you.
No, sir.
Right. So we will move on to potential, guys. So in the as we solve problems, I will give some tables also there. I may not have free time till 22nd, 21st, 22nd, guys. But after that, I'll sit, and most probably by 30th April, right, I will try to give the entire synopsis chapter wise, so that in the last week, right, you can focus daily 3, 3, 4 chapters. You can review again, so that for the exam it will be helpful again. I'll share that for sure. Right. So let us move on to electric potential and capacitance, guys. Already problems are ready. So we will discuss those problems. That's not a big deal. So let us move on to electric potential and capacitance. It is also very small, right? So we will quickly discuss that. Now, what is the meaning of potential basically, right? So if I take a test charge, I am bringing it somewhere from infinity to a given point. Whatever the amount of work is done in bringing a test charge from infinity to a given point is called as electric potential. Potential difference is nothing but you are taking a test charge, bringing it from one point to the other point. That will be called as electric potential difference. So as you can see, the electric potential is basically, it is the work done against the electric field. It means work is done by an external agent in moving a test charge from where to where, from infinity to a given point. So this would be the expression, or you can say the expression for potential, or in general you can also write gravitational potential as electric potential as electric potential energy per test charge, guys. This is very important formula again. And when I say electric potential energy, let us take two charges. Here we have q1 and q2. Let us imagine both are separated by some r distance. So whenever two charges are separated by r distance, the electric potential energy will be given as k into, here in this case, in force, we took only magnitude, guys. But whereas when you are finding electric potential energy, you should take however the charges are. With polarities you should take. So I'll directly write k q1 q2 divided by r. Okay. This is potential energy. Suppose I want to find potential at this point. I'll name the points as 1 and 2, guys. This is for understanding purpose. So I want to find potential at point 1, let us say. What will potential at point 1 be? It will be potential energy at that point divided by the charge placed at that point. So I'll get it as kq2 divided by r. Similarly, I want to find potential at second point. So potential at first point will be 0 due to q1 charge. It will be kq2 by r due to second charge. Similarly, I can write it as u divided by q2 beta. What will I get? kq1 divided by r. For force calculation, you will take only magnitude of charges. For potential energy calculation or potential calculation, however the charge is given, you will take in the same manner. If it is negative charge, you will take negative. If it is positive, you will take positive. Clear? So some basic things you should know again. uh, for a short point charge, you can take it is kq by r. For a dipole, short dipole, if you take at an axial point, it will be given as kp cos theta divided by r square, or in general, for a short dipole, it will be given as k p bar dot r bar divided by r cube, guys. If I am not wrong, it will be given as k p bar dot r bar whole divided by r cube, right? And for a short dipole only, they will ask you basically potential will be kp cos theta by r square. In reality, it is given as k p bar dot r bar divided by r cube. Principle of superposition is valid for potential. Suppose I want to find potential at point P due to system of charges. So what is it due to point charge? Kq by r, you know. So what will it be due to Q1? Kq by R1. What will it be due to Q2? Kq2 by R2. What will it be due to Q3? Kq3 by R3. So the total potential at point P will be algebraic sum of potential due to all the charges present in the system, guys. So I can write it as potential due to first charge, potential due to second charge, potential due to third charge, potential due to n number of combination of charges, guys. So potential due to system of point charges. This is nothing but your principle of superposition, guys. Clear, all of you? So majorly remember this. You should also remember for spherical shell, non-conducting solid sphere, right? We cannot define potential for line charge and for plane charge. We can define only potential difference, guys. Those also we should remember again. But let us not focus on those points because majorly they have not been asked, guys. However, in tomorrow's class, when we are doing problems, somewhere or the other way, they will be asked. So I'll give a table tomorrow. Okay. So basically, potential is, it is the amount of work done in bringing a unit positive charge, which is test charge, from infinity to a point. From one point to another point will be called as electric potential difference, guys. So as you can see, work done against electric field from one point to another will be called as electric potential difference, and we can consider that to be, I'll just apply limits here. So in the previous case, you can see electric potential, I wrote from infinity to a given point, as you can see. Limits have been applied. What is minus sign indicating? Minus sign is indicating that I am doing work against electric field. So limits are applied from infinity to r. Whereas in potential difference, guys, they will be applied from some r1 to r2. As you can see, they will be applied from some r1 to r2. Clear? So I can also write the potential difference as delta V. I can write it as change in potential energy divided by charge. It is also very, very important. Just like we have written potential as U by Q, potential difference will be delta U divided by Q. And always remember, right, if you take 2 points, guys, you may move in any path between those 2 points because potential is a scalar quantity, right? It will be path independent, guys. So as you can see, the potential difference does not depend on path. So here you have 1 point, here you have 1 point, or a charge is taken from here to here. Let us say in different paths it may be taken. Potential difference in all the paths will be same. State function it is, just like internal energy is a state function. Clear, all of you? Relation between electric field and potential is also very, very important. Again, what is the relation in general? If I'm writing over here, electric field is given as minus of dV divided by dr r cap beta. So what is minus sign indicating? Electric field lines will always be in the direction of decreasing electric potential. Minus sign indicates that electric field lines will always be in the direction of decreasing electric potential. So very important thing, guys. If potential is only varying with x, I will write, means only along with x if it is varying, I will write it as minus of dV by dx I cap. If potential is varying only with y beta, then I will write electric field as only minus of dV divided by dy j cap. If it is varying only with z, guys, then I will write electric field as only minus of dV divided by dz k cap. Differentiation is used for small changes. So as it has been written here, guys, electric field next direction will be minus dV by dx I cap, electric field in y direction minus dV by dy j cap, electric field in z direction minus of dV by dz. Suppose if potential is varying with all x, y and z, guys, then I'm going to make use of partial differentiation. Electric field will be given as minus of dou v divided by dou x I cap plus dou v divided by dou y j cap plus dou v divided by dou z k cap. So here dou stands for partial differentiation, d stands for complete differentiation. When I am doing partial differentiation with respect to x, only x should be taken as variable. When I am doing partial differentiation with respect to y, only y should be taken as variable, rest all should be considered as constant. In the same manner, when you are doing partial differentiation with respect to z, only z should be considered as variable, rest all should be considered as constants. So this is electric field again. And how can we write potential beta? Potential, it will be given as, so we basically will use this formula again. dV will be given as minus of E bar dot dr bar. If I want to find potential difference, what I will do, beta? I'm simply going to apply limits again. So if I want to find potential difference, I will write V1 to V2. If I want to find potential, I will use infinity to R, guys. And always remember, in case of electrostatics, we will assume infinity to be zero potential level or zero potential energy level, guys. Clear, all of you? Yes or no? Right. So if we talk about equipotential surface, it is a surface at all points on which potential should remain same, guys. And very important point that we have, electric lines of force, whatever we are taking, they should always be perpendicular to equipotential surfaces. Whatever electric lines of forces we are taking, they should always be perpendicular to the equipotential surfaces, guys. So for point charge, you will have spherical equipotential surfaces. For line charge, you will have cylindrical. For uniform field, if you take, means it is for planar charge, guys, or plane sheet of charge, you are going to have planar surfaces. So these points you should remember. Equipotential surfaces are those surfaces at all points on which potential has to remain same. For point charge, they will be spherical in shape. For line charge, they will be cylindrical in shape. And for a plane sheet of charge, which will give us uniform field, they are going to be planar in shape. I have already told you regarding electric potential energy, but one point I have not told you, if you have two masses, we got one pair. In the same manner, if we have n charge system, we took two charges, guys, we got one pair. If you have an n charge system, how many pairs of electric potential energy will be there? Again, n minus n by n minus n into n minus 1 by 2 pairs of electric potential energy will be there, guys. If you have two charges directly, only one pair. But if you have n charges, guys, then you are going to have n into n minus 1 by 2 pairs of electric potential energy. Clear, all of you? Yes or no? Right. So let us talk about conductors as well as capacitance. Maybe that will be completed in another 30 odd minutes, guys, because direct questions you will get from capacitances. Let us focus majorly on doing questions only. So if we talk about conductor, again, conductor is, you can take any element or material which has large amount of charge carriers, guys. It is going to have large amount of charge carriers. So some properties, if you see, inside a conductor, always remember electric field line is, electrostatic field is zero, means inside the conductor equipotential surfaces can be of any shape, guys. Okay. And at the surface of charged conductor, always remember, at the surface, how should electric field lines be? They should be perpendicular, guys. Near to the surface of the conductor, electric field line should always be, electrostatic field must be perpendicular to the surface. Very important point, right? So inside the conductor, right, the charge density will remain zero, because inside you don't have any field. Field is not there, means charge should not be there. So all the charges in the conductor will be distributed on their surface. There will not be any charge present inside the conductor. They will be distributed on the surface. So conductor is equipotential, it seems. Just now I said, because electric field inside the conductor is zero, you take any point, potential will be same. Everywhere inside the conductor, potential will be same. So that is the reason equipotential surfaces can be of any shape. And just near to the surface, it's a very very important point, guys, just near to the surface of the conductor, electric field will be given as sigma divided by epsilon naught. There is a proof also for this, let us not focus on it, but very close to the surface, electrostatic field line should be perpendicular to the surface of the conductor. And how much will be the electric field line? It will be sigma divided by epsilon naught. Clear, all of you? Understood, everyone? Let us not focus on electrostatic shielding. The question has not been asked, right, any time. So we will not focus on electrostatic shielding. However, if I can just read out the statement for you people, if conductor has a cavity with no charge inside the cavity, then electric field inside the cavity is zero. You can do it by Gauss law again, right? So what we can do is, suppose if you take a car, you're sitting in a car, guys, and suddenly what we can consider, what do बिजली को क्या बोलते हैं वर्ड कहीं नहीं आ रहा अभी तो ठीक है वॉट एवर इट इज రైట్ ఏమంటారు అవి పిడుగు పడుతుంది పిడుగేనా ఇంగ్లీష్లో ఏమంటారు
Understood.
thunderstorm अच्छा okay thunderstorm is it thunderstorm you can say it is lightning only no right so suppose if we say pidugu is falling pidugu pad raha hai aapki gaadi pe then in that case you are sitting in a box you can imagine right the whole charge is distributed on the surface only inside you don't have any charge so you will never get electrocuted guys if you are sitting inside why again it is the process of electrostatic shielding only so if there is no charge inside the cavity what is Gauss law stating flux through any surface is q enclosed divided by epsilon naught if there is no charge there is no flux means no electric field so inside electric field is not there means there will not be any conduction only so in a conductor if a conductor has cavity what they are saying if conductor has cavity and if there is no charge in the cavity with no charge then what is electric field inside the cavity zero so whatever be the charge it will be on the surface or it will be outside the conductor guys so this phenomena is basically called as shielding effect or electrostatic shielding we call okay it's not that much necessary again so this is one part of electric charges and fields the other part happens to be capacitance let us have a review of that quickly the capacitor is the device which stores electrical energy guys what is it it is a device used to store electrical energy how it will store in the form of electric field you can say or electric charge it is better if you say electric charge so what is capacitance how much charge it is able to store the ability of a capacitor to store charge will be measured by its capacitance and we have just now seen potential due to a point charge is given as kq by r so as charge is increasing potential is increasing so whenever you are giving more charge its potential will increase so what we can write the charge stored on the capacitor can be written as c into v or I can write capacitance value as q divided by v even though it is written as q divided by v it is very important point guys it is independent of charge and potential difference capacitance will be independent of charge and potential difference what does it depend on it depends only on medium surrounding the plates and shape and size of the plates guys so as you can see right it depends only on shape and size of the plates and medium surrounding the plates even though it is given by ratio of charge to potential difference it will neither depend on charge nor on potential difference capacitance will only depend on shape and size of the plates as well as medium surrounding the conducting plates unit is given as farad guys but farad happens to be generally a large unit that is the reason we make use of microfarad instead of using farad again so if you have a isolated spherical conductor directly I am writing again for an isolated spherical conductor whose radius is r capacitance will be given as 4 pi epsilon naught r very important again only one spherical conductor is there so its capacitance will be 4 pi epsilon naught r and if you consider earth to be an isolated spherical conductor for earth capacitance will be 711 microfarad okay in the same manner guys capacitance of a parallel plate capacitor if we talk about so only isolated sphere is there capacitance will be 4 pi epsilon naught r so if you talk about parallel plate capacitor guys in between the plates you are going to have uniform field that field will be given as sigma by epsilon naught or q by a epsilon naught so what is potential difference given as potential difference directly will be given as e into separation between the plates guys so what you will get so if I write potential difference here between the plates it is directly given as e into delta x we write separation between the plates is here d so we'll get it as qd by epsilon naught or sigma d by epsilon naught You got the potential difference. So can you find out charge again? Charge so anyhow is given. So what will I get capacitance value? This is potential difference, guys. Potential difference is q d by epsilon naught a. So I can write q by delta v as epsilon naught a by d. So the capacitance of the capacitor will be given as epsilon naught a divided by d. Right? What will happen? Between the plates, there will be some force of attraction. That force of attraction will be given as half q into E, or q square divided by 2 epsilon naught, or sigma square a divided by 2 epsilon naught, guys. That there will be force of attraction between the plates. I'm not deriving all these, guys. Please remember, between the plates of the capacitor, you will have a uniform field given as q by a epsilon naught or sigma by epsilon naught. Because it is a uniform field, potential difference will directly be given as the electric field into separation between 2 points. So electric field we already got. So I'll write potential difference as q d by a epsilon naught. So from this, the ratio of q by delta v is nothing but capacitance. So you'll get it as epsilon naught a by d. Both the plates will attract each other, guys. So force of attraction between the plates will be half into q into e, or q square by 2a epsilon naught, or sigma square a divided by 2 epsilon naught, guys. We'll also talk about the effect of dielectric here. So whenever a dielectric slab has been placed whose thickness is t, let us consider, then capacitance of the capacitor with dielectric will be given as epsilon naught a divided by d minus t plus t by k, guys. This would be the effective length again. So on the inside the dielectric, you are going to have charge distribution. This is called as polarization of charges, guys. Right? So it will be dealing with dielectrics again. So induced charge will be developed within inside the surfaces of the dielectric slab. The charges will be developed. Those charges are called as which charges, beta? Minus q and qi are our induced charges. So basically they are going to be given as charge into 1 minus 1 by k again. So whenever a part of this, or the space between the plates of the capacitor, only part of the space between the plates of the capacitor is filled with a dielectric whose thickness is t and dielectric constant k, then capacitance will be given as epsilon naught a divided by d minus t plus t by k. Now, as I said, if you have a metal dielectric, guys, if the material is metal, metal means it is a perfect conductor again. So that is the reason the dielectric constant value will be infinity for that. So for conducting slab, you can take the capacitance will be epsilon naught a divided by d minus t, guys. Okay. So although that is not required, you please remember these two formulas. If space between the plates is free space, epsilon naught a by d. If space between the plates is partly filled with dielectric, you will get epsilon naught a divided by d minus t plus k. If fully filled, again, if I say, if space between the plates is completely filled with dielectric, guys, if space between the plates is completely filled with dielectric. So if it is completely filled with dielectric means, will thickness become equal to distance or not? So what is the condition here? D value will be equal to T again, or T value will be equal to D again. So what are we going to get the capacitance as? I'll get the capacitance as K epsilon naught A divided by D. So what is happening to the new capacitance, guys? It is becoming K times the actual capacitance. So if you are, see, very important, between the space of the capacitors, if a dielectric is being filled, irrespective of it being filled completely or partly, capacitance of the capacitor will increase. If it is completely filled, then it will increase by k times, guys. If it is partly filled, then you can follow epsilon naught a divided by d minus t plus t by k. Clear? Right? Isolated sphere capacitance 4 pi epsilon naught r. Okay, for earth 711 microfarad. Spherical capacitors means two hollow spheres, one positive charge, other negative charge, are connected to each other such that outer surface is silvered, guys. So if outer surface is silvered, I am going to get the capacitance as 4 pi epsilon naught ab divided by b minus a. A is the inner radius, b is the outer radius, and 4 pi epsilon naught, as you all know. Suppose if inner surface is silvered, guys, then it will be given as 4 pi epsilon naught b square divided by b minus a. Okay. Again, there is a proof for that, but as of now, let us not focus on that. Isolated spherical capacitor, 4 pi epsilon naught R. Spherical capacitor, if I take 4 pi epsilon naught AB divided by B minus A, for which silvered, guys? Outer surface is silvered in this case. So if outer surface is silvered, 4 pi epsilon naught AB divided by B minus A. If inner surface is silvered, 4 pi epsilon naught B square divided by B minus A again. In the same manner, if you take cylindrical capacitor also, please remember potential difference also, guys. If we talk about potential at any arbitrary point, you take this point P. It is lying outside the inner sphere. Because point is outside, I can concentrate the whole charge of the sphere at its center. So I'll get potential at point P as, due to inner shell, KQ by R. But due to outer shell, if I take, right, outer shell, is it present inside the outer shell or not? Yes, it is present inside the outer shell. Outer shell has how much charge? Minus Q. So what will I write? K into minus Q divided by B you will write. So potential at point P will be KQ by R minus KQ divided by B. Right? Now you will substitute, you will perform, you will find potential at this point. First point you will find potential. If you are finding potential at first point, R value will be A. Then you will find potential at second point. R value will be equal to B. From there you will find potential difference. You will get it as some value, you will get potential difference. So charge by potential difference will be nothing but your capacitance again. So it is given as 4 pi epsilon naught AB divided by B minus A, guys. Clear all of you? Understood everyone? Is that clear everyone?
So यहाँ पे silver means earthed.
यहाँ पे
Does silvered means earthed?
सिल्वर्ड नहीं, सॉरी, सिल्वर्ड क्यों लिख दिया मैंने? If outer surface is earthed, I'm sorry, अभी मैं ray optics में हूँ. Right. If outer surface is earthed, then capacitance will be 4 pi epsilon naught AB divided by B minus A. If inner surface is earthed, guys, it will be given as 4 pi epsilon naught B square divided by B minus A. Cylindrical capacitor in the same manner, it will be just like a line charge. For line charge, how will we do? We will do the proof in the same manner for cylindrical capacitor, and its capacitance will be given as 2 pi epsilon naught L ln of outer radius divided by inner radius. Very important case again. 2 pi epsilon naught L divided by ln of B divided by A. All the other things are not that much necessary, guys. However, potential difference, if you can remember, that would be better. Potential difference will be 2kQ by L ln B by A. So Q by V can directly be written as C only. Okay. Let us talk about dielectric polarization. So whenever a dielectric medium is placed between the plates, as I said just now, polarization of charges will take place. So initially, in the absence of external field, guys, positive charge center and negative charge center will coincide on each other. As soon as you turn on the electric field, if you are placing a dielectric in an external field, positive charges are going to, they are going to get aligned in the direction of electric field. Negative charges are going to get aligned opposite direction of electric field. So in the absence of electric field, positive charge center and negative charge center will coincide. But in the presence of electric field, guys, all the positive charges will move in the direction of electric field, negative charges will move opposite direction of electric field, thereby producing a certain field again directed from positive to negative charge. This will be your induced field that we basically considered. So these charges will be called as your induced charges, guys. Okay, so the induced charges developed will be q into 1 minus 1 by k. Here you still have free space only, guys. So in free space you will have a field of E naught, whereas in this space what are we going to have? You are going to have a field of E naught divided by k. Okay, this is the situation. Inside the dielectric, electric field will get reduced by k times. Always remember this, right? For a dielectric, what will happen? The electric field will get reduced by k times compared to the field outside or compared to the field in vacuum or air, guys. Okay, so this is very important case, guys. So basically, if I take, if entire space between the plates is filled with a dielectric, we got capacitance as K epsilon naught A by D. Yes or no? If entire space is filled. Now I can write it in two ways, guys. Can I write it as? Can I write it as epsilon naught by D K into A? Do you have any trouble? Can I also write it as, right? I can write it as epsilon naught A divided by D by K. Do you have any trouble, guys? Both the cases are same only, no? I'm just writing it in that manner. So this will be the situation if D is same, guys. Distance between them is same. This will be the situation if area of cross section is same. So when will distance be same? If you are placing the dielectrics vertically, guys, or you can consider the dielectrics are held vertically like this. Clear, all of you? In the same manner, in this case, area of cross section is same. Sorry, if they are held vertically, area of cross section is same. If you are holding it horizontally, if you are inserting the dielectric horizontally, then distance is, so dielectrics are filled horizontally, let us say. So when dielectrics are filled horizontally, in that case, separation between the plates will be same, right? What we can write it as epsilon naught by D K into A. And when will area of cross section be same, beta? When dielectrics are filled vertically. So if dielectrics are filled vertically, what will remain same? Area of cross section will remain same. For one dielectric only I am talking about. So dielectrics are filled vertically. If dielectrics are filled vertically, area will remain same. Now you see, in this case, are dielectrics filled vertically? Yes. So for this is one capacitor now. This will be another capacitor. This will be another capacitor. This will be another capacitor. So if I assume this is one capacitor, I'll get T1 divided by K1. Here you will get T2 divided by K2. It's not visible. If I consider this to be one capacitor, guys, you will get this as T1 by K1. Similarly, this you will get it as T2 by K2. This you will get it as T3 by K3. This you will get it as T4 by K4. If you had only one capacitor, it was written as D by K. When you are filling the dielectrics vertically, area of cross section will remain constant. So only one capacitor is there, you wrote D by K. Now you have four capacitors. So you will write D1 by K1 plus D2 by K2 plus D3 by K3 plus D4 by K4, as you can see here directly. Direct step, guys. Whenever dielectrics are filled vertically, area of cross section will remain same. So I'll write capacitance as epsilon naught A divided by, if only one dielectric is filled, you'll write D by K. If number of dielectrics are filled, I'll write D1 by K1 plus D2 by K2 plus D3 by K3 plus D4 by K4 plus so on. Right? In the same manner, let us say if the dielectrics are filled horizontally, as you can see in this case. So what will happen? D is same. So as D is same, for one dielectric if you take, guys, D is same. For one dielectric if you take, what will I get? Epsilon naught by D K into A. But when different set of dielectrics are placed horizontally, then I'll write capacitance as epsilon naught by D K1A1 plus K2A2 plus K3A3 plus so on. So as you can see here, guys, देखो, epsilon naught by D common, K1A1 plus K2A2 plus K3A3 plus so on. Clear, all of you? Always remember, whenever dielectrics are placed vertically, if they are filled vertically, area of cross section will remain same, epsilon naught A divided by D1 by K1 plus D2 by K2 plus D3 by K3 plus so on. If they are filled horizontally, distance will remain same. So epsilon naught by D K1A1 plus K2A2 plus K3A3 plus so on. Clear, all of you? Yes or no? Next, we have combination of capacitors. We are almost at the end, guys. Majorly, we have to solve questions only, which we will do tomorrow and after tomorrow. So capacitance in series, when we consider series combination, when will you say series combination, guys? It is not necessary that only charge should be constant, right? So charge flowing through all the capacitors or charge stored in all the capacitors should be constant. Okay, that is acceptable. But there should also be a end-to-end connect, guys. My voice is not audible. Hello, check 1 2 3. Am I audible? I'm audible. Maria,
Yes.
please. Right. So you please try to understand here. When can I say capacitors are in series combination? Right, in series combination, majorly we know charge should be constant. Okay, charge stored in all the capacitors should be constant. But just this condition will not be sufficient to say it is series combination, guys. Charge should be constant, and also there should be a end-to-end encryption you have no in WhatsApp. So here you should have a end-to-end connect, guys. One end of first capacitor should be connected to one end of the second capacitor. Similarly, one end of the second capacitor should be connected to one end of the third capacitor. So already charge flowing or charge stored in all the capacitors will be same in series combination. But apart from that, there should be end-to-end connect. Then only they will be in series combination. And in series combination, I can write 1 by C effective will be 1 by C1 plus 1 by C2 plus 1 by C3. So what will get distributed here? Charge is constant or not, guys? So as I can say, if charge is constant, Q1 value will be equal to Q2. So I can write C1 V1 will be equal to C2 V2. Potential differences are going to get distributed in the inverse ratio of their capacitances, guys. If I take two capacitors, so I'll get V1 value as C2 into V divided by C1 plus C2, and V2 value I'll get it as C1 into V divided by C1 plus C2. Okay. So in series combination, charge stored should be same in all the capacitors, and there should be end-to-end connect. And how will potential difference get divided? Potential difference will get divided in the inverse ratio of their capacities, guys. Okay. Parallel combination. When will you get parallel combination? I'm not explaining two cases again, two capacitors cases, guys. When will you get parallel combination? Right, all the capacitors should be connected between two same points, guys. As you can see in this case, first capacitor is connected between these 2 points, second also between same points, third also between same points. So whenever capacitors are connected between two same points, such type of combination blindly will be a parallel combination. And in parallel combination, what will remain same? V is not potential here, guys. It is potential difference is constant. So as potential difference is same, I can write V1 value will be equal to V2. Means I can write Q1 by C1 will be equal to Q2 by C2. So how will charge get distributed, beta? It will get distributed in the ratio of their capacities. How will it get distributed? In the ratio of their capacities. The effective uh, capacitance will be algebraic sum of individual capacities, guys. C1 plus C2 plus C3 plus so on. So what will be charge Q1 here? It will be C1 into total charge divided by C1 plus C2. What will be charge Q2 here? C2 into total charge divided by C1 plus C2. Clear? This would be capacitors in parallel. So in series, exactly reverse of resistors, guys. In series, 1 by C effective will be 1 by C1 plus 1 by C2 plus 1 by C3 plus so on. In parallel, you will have C1 plus C2 plus C3 plus so on. So if n identical capacitors are connected in series, effective capacitance will become C by n. But if n capacitors are connected in parallel, effective capacitance will become n times of C. Similarly, as I have said in the very beginning, capacitor is a device which is going to store electrical energy. And the energy stored in the capacitor will be given as half CV square or half Q into V or Q square divided by 2C again. Now, this is a very important case, guys, right? Because previous year questions have been asked from capacitors based on sharing of charge. Always remember one thing. Sharing of charge will take place between two objects only if there is potential difference between them. Sharing of charge will take place between two objects only if there is potential difference between them. If there is no potential difference, then sharing of charge will not take place. Sharing of charge will stop until both the objects are going to reach a common potential. So already if two objects are at common potential, will sharing of charge take place? No. Sharing of charge will take place only when there is potential difference, and that too, the charge will flow from higher potential to lower potential. So initially two isolated capacitors, guys. This is initially a separate capacitor. This is also initially a separate capacitor. Both are charged to some different potential difference. Let us imagine, just imagine V1 is greater than V2, guys. As soon as the switch is closed, now charge will start to flow. If V1 is greater than V2, charge will start to flow from here to here, right? How much charge? Some Q charge, let us say, is starting to flow, guys. Till what extent will charge start to flow? Until both of them will attain a common potential, right? And as you can see, like polarities are connected together after closing of switch. So common potential will be C1 V1 plus C2 V2 divided by C1 plus C2. And how much charge will be flown, beta? It will be C1 C2 divided by C1 plus C2 into V1 minus V2. From where to where? From A to B if V1 is greater than V2 again. And there will also be some loss in energy in this case, which is found out by using initial energy minus final energy, which is half C1 C2 divided by C1 plus C2 into, if like plates are connected, V1 minus V2. If unlike plates are connected, V1 plus V2, guys. Okay, this would be the sharing of charge. Sharing of charge, always remember, sharing of charge will take place if there is potential difference. And sharing of charge will always take place from higher potential to lower potential until both of them attain common potential. Once both of them attain common potential, sharing of charge will stop. So basically, it is based on conservation of charge, guys. It is based on what? Conservation of charge. Charge will remain conserved. Please tell me, before closing the switch, what is the charge with C1? C1 V1. What is the charge with C2? C2 V2. This is the before closing the switch. After closing, they will share the charge, attain a common potential. Both of them will have common potential. So what I can say, C1 into V plus C2 into V. So what will that common potential be, beta? C1 V1 plus C2 V2 divided by C1 plus C2. This would be the common potential. In the same manner, charge, how much charge is flowing means, initially here it is C1V. Now it became C1 initially it was C1V1. Now it became C1V. So difference between these two or difference between these two will give us the amount of charge flowing. There will be loss of energy given as half C1 C2 divided by C1 plus C2 into V1 minus V2 whole square. In the same manner, if unlike plates are connected together, as you can see in second case, if unlike plates are connected together, as soon as you close this switch, guys, they are going to attain common potential. That common potential will be C1 V1 minus C2 V2 divided by C1 plus C2, and loss in energy will be half C1 C2 divided by C1 plus C2 into V1 plus V2 whole square. There it is C1 V1 plus C2 V2. Here it is C1 V1 minus C2 V2. There it is V1 minus V2. Here it is V1 plus V2 whole square. Clear, all of you? Yes or no? Now, effect of inserting dielectric slab is important, guys. So let us say if the capacitor is isolated, okay. So inserting a dielectric slab when capacitor is isolated means it is not connected to battery. Charged capacitor, let us say, is isolated. So in that case, what will happen? As soon as you completely fill the space between the plates with a dielectric slab, capacitance will neither depend on potential difference nor on charge. It will depend only on the properties again. Yes or no? So what is going to happen? As soon as you entirely fill the space with a dielectric, as I have said just now, capacitance will increase by k times. So you see, new capacitance became kc naught. Now please tell me, charge is always given by battery, guys. In first case, where capacitor is isolated, do we have a battery which will give some extra charge, guys? No. So that is the reason in this situation, charge on each plate remains same. Because I don't have the external source to provide charge to the capacitor, charge stored on the capacitor will remain same. Capacitance got increased by k times. So automatically potential difference will get reduced by k times. Energy also will get reduced by k times, guys. This is very important. In next case, is it connected to battery source? Yes, it is connected to battery source and dielectric is being inserted. Before being inserted, it is connected to same battery source. Even after being inserted, it is again connected to the same battery source. So whenever it is connected to same battery source, what will remain same, guys? Voltage is constant. Now, whenever dielectric is inserted between the plates, capacitance will increase or not. So capacitance got increased, potential difference constant. So automatically charge will also become K times, guys. And potential energy will also become K times. Clear, all of you? Understood, everyone? Yes or no? In first case, capacitor is isolated. When capacitor is isolated, dielectric is inserted. There is no battery to produce charge. So charge will remain constant. As soon as you insert the dielectric, capacitance value will increase. So capacitance got increased by K times. Charge constant, capacitance is increasing by K times means potential difference will get reduced by K times. Energy will get reduced by K times. In the same manner, what will happen if it is connected to the battery source and inserting the dielectric is being inserted? Previously, before insertion of dielectric, same battery source. After insertion of dielectric, again same battery source. So potential difference across the plates will remain same. Capacitance anyhow is increasing. So charge will also increase and energy stored will also increase. Clear, all of you? Understood, everyone? The last case that we have is combining of, what happened to this? Right, so we have combining of charge drops, guys. It is the same principle that will be used in surface tension also. Suppose if you take n small drops, let us say they have a charge, they have already given radius is taken as r naught, charge is q naught, each has a capacitance, let us say c naught, guys. N drops, each capacitance is c naught. Now, all these are combined to form a large drop, first and foremost. And what is the radius of the large drop? It has been taken as capital R. First and foremost, in this situation, volume is conserved. What is conserved, beta? Volume is conserved. So if I use volume conservation principle, I will get relation between the radii. What is the relation between the radii? Large radius, larger drop radius is n power 1 by 3 times of smaller drop radius. Capacitance for an isolated capacitor is given as 4 pi epsilon naught r. Now, what will be the new capacitance? Because radius became n power 1 by 3 times, capacitance will also become n power 1 by 3 times. Volume is conserved. Also in this case, charge is conserved, guys. These two principles are used in combination of charges. So because charge is conserved, initially and finally charge will be same. So initially each drop had q naught charge. So total charge will be n into q naught. Finally also this will have n into q naught. Capacitance became n power 1 by 3 times. Charge became n times. So automatically potential difference will become n power 2 by 3 times and energy will become n power 5 by 3 times. These points you should definitely remember. The principle of solving questions for sharing of charge, what is the principle? Sharing of charge will take place if there is potential difference and charge always flows from higher potential to lower potential. Sharing of charge will stop until both the objects reach common potential. In combining of charge, what is the concept? Whenever small drops are combining to form large drop, volume will be conserved in this case and charge will also be conserved in this case. Clear? So please remember what will happen to the capacitance. It becomes n power 1 by 3 times. Charge will become n times the capacitance, n times the charge of each small drop. Potential difference will become n power 2 by 3 times. Energy stored with the large drop will become n power 5 by 3 times the initial energy stored with each drop. Clear? So please remember few things again. Basic important things are last three things, guys. Combination of charges, right? What will happen to the capacitor when dielectric slab is being inserted? If the capacitor is isolated, if it is connected to battery source, and sharing of charge. Majorly, these are the three areas where questions will be asked from capacitors. Clear, all of you? And in general, combination of capacitors, energy stored in capacitor, these are anyhow basic cases which we can understand. Clear, everyone? Some more extra additional points are there that are to be discussed, guys, but those we will discuss along with the problems only. Okay. I am getting some notifications of 1800. Guys, I am requesting you, please don't share the fees as of now. I am going to give the details of that. Please don't send any amount, guys. It's a humble request. I'll let you know, then you can send.
Sir,
Please, sir.
sir, what will be the angle between equipotential surface and line of force?
90 degrees, close to the surface. They will basically be perpendicular only. So electric lines of force will always be perpendicular to equipotential surfaces. Okay, 90 degrees. Next, please. Any doubt in this, all of you? So let us discuss majorly with problems. I have just given a quick review what is happening, what is not happening, right, in both electric charges and fields as well as electric potential and capacitance. Tomorrow we will be doing, and hopefully day after tomorrow we'll be doing questions on electrostatics. If possible, if they are completed quickly, then day after tomorrow I'll start current electricity. Clear all of
Sir,
you?
uh,
Ask.
sir, when A and B are two circles,
Hmm,
like and A having A is inner concentric sphere and B is outer concentric sphere.
hmm,
A is having positive charge.
hmm.
When B is Earth, then what will be the electric field between A and B?
Charge is given.
Yes, positive charge is given on A, inner concentric sphere.
So you're saying something like this. This is one sphere in the same manner. But you can consider there is one more sphere, something like this. Yes.
Yes, sir.
Hmm. A is given, B is given. Okay, only A has charge.
Yes, only A has charge and B is Earth.
It is a case just now we have done. No? How much charge is given?
So no charge is given. Just
Hmm?
it's asking what is the electric field between A and B.
Conceptual. Matlab, any word is given or what?
Only conceptual. Only it is given that A and B are two concentric spheres. If A is given charge
No, I
A,
understood the question. How much is the charge given to A?
is no charge is given. So only positive charge
No,
is given. That's
ठीक है,
it.
positive charge दिया. So options are statements, I guess then.
Yes, sir.
हाँ, to tell those statements instead of without telling the statements, how can I solve the question then?
Charge densities of A and B are same.
Mm-hmm.
Electric field inside and outside A is zero.
Electric field,
Inside and outside inside and outside A is zero.
both are conductors given us.
Yes, sir.
So you see, one basic logic that we will use is, I will just consider. See, I'll just take inside here. One Gaussian surface I'll take inside. Let us imagine some charge Q is taken on the surface of the A. Okay. And you take here, just inside you take. I'm taking Gaussian surface, just inside. Just inside means, is it inside the conductor or not? Inside the conductor, how much is the field? Zero. So field is zero means, should there be any charge? No.
No.
So inside the conductor, you are not going to have any charge. Inside A, inner surface of A, no charge. So the whole charge will be on the surface of A only, that is Q. Now I'll take one more Gaussian surface which is here inside. Just inside B I am taking. How much should be the electric field here? How much should be the electric field? Because it is inside the conductor only again. So how much should be the electric field?
Zero.
Zero. So electric field is zero means charge enclosed should also be zero. But I
Zero.
have positive charge. So what will happen? In within inner surface, I should get a equal negative charge deposited on the surface. I should get a equal negative charge deposited on the surface. So if I take this to have plus q charge, here you are going to have minus q charge. Clear? And what is the other thing? Right. B is uncharged, no? B is uncharged. Sharing of charge will take place again. So B is uncharged means you please try to understand. Total charge of B should be 0. So total charge of B should be 0. Inner surface it has minus Q charge. So on the outer surface it will become plus Q again. Okay. So now you try to understand at point P. Let us take a point P which is inside, which is somewhere over here. Point P is outside inner shell. So due to the net field at point P, if I find out, because it is inside the inner shell, let us say it is at a certain distance r. So due to the inner shell, it will be kq divided by r. Whereas it is inside the outer shell. Inside the outer shell, it will be 0. So electric field at point P will be kq divided by r. Now you tell me what are the options. You understood how charge distribution is taking place?
Yes, yes, sir.
So now I think you can get whatever option statements are there, you just read them out and just check it whichever is the correct answer.
So shouldn't it be R square?
क्या है? अरे यार तू ये लो हो गया खुश खुश
The
वैष्णव.
first option is
Yes.
charge densities of
Hmm.
A and B are same.
Hmm.
Second is electric field inside and outside A is 0.
Electric field inside and
Outside A
electric
is
field
0.
inside A is 0. Outside A you will have electric field due to A.
Okay.
Here you will have kq by r square you will get. Hmm.
Third is the electric field between A and B is non-zero.
Non-zero it is kq by r square. Correct.
Fourth is electric field inside and outside B is 0.
Inside and outside B, no, it will be kq by r square again. If you take inside B, there is field due to A. Outside also there will be field due to A charge. Due to B you may not have, but due to A, if I take Gaussian surface, again you will get kq divided by r square. So there is field inside B, there is field outside B. Okay. So I think
Okay.
third option may be most probable answer.
Okay.
First option, why it is not correct? Because their volumes are not same. Although charges may be same, but volumes are not same. So their densities will not be equal. Right. So tomorrow we will discuss the questions. How many ever are possible, I'll try to discuss, guys. And let us hope. And what I have requested you, please share it, guys. I've asked you people to share the email IDs. Please do share so that I can work on it. Okay. Any doubt, all of you? Any other doubt, everyone?
No, sir.